Okay, guys, in this video lesson, we're going to start talking about Kepler and how he was able to determine or build three laws of planetary motion for us. Okay, so to do that, we want to back up one little step to remind us that Kepler didn't really do the research himself. He got that research from Tycho Brahe, and he was able to take that data that Tycho had basically compiled and is able to now take that information and put it into these different three laws of motion. So Kepler was a mathematician using math. He did this. So first law, orbits of planets are elliptical with the sun at the foci. Okay, so at this point in history, there was a lot of intermingling of faith, religion, science, government, politics, that kind of stuff. All kind of played a role here. And for a person to come out and say that the planetary motion isn't a circle is kind of a big deal. Okay. The idea of a circle being perfect, being never ending, being the equal distance from a center, it had kind of a divine kind of meaning behind it. So to come out and say, hey, no, it's not a circle, it's an ellipse, is kind of a throwing, hey, it's not perfect. There's actually a little bit of a warp to this. And that's okay, because mathematically we can show it and we can kind of prove it's that way. All right. So that's what the first law is really doing is basically saying it's not a circle, people. It's elliptical is our orbit that we're going to. Okay. We'll jump to a flash drive here in a second. I want to cover the second law before we get to that point first. The second law Kepler put out for us was that we have this line. If you join a line from the sun to your planet or any satellite really, the area that it sweeps out in a given amount of time. So if this is 1 month, 2 months, 3 months, 4 months, 5 months, 6 months, and so forth and so on, the area in blue here is equal to the area in blue here, which is equal to this area here, which is equal to this area here, and so forth and so on. Okay? For that to be true, if the planet moves from here all the way to here, in the same amount of time, it only goes from here to here, when it's a lot further away from the sun, that gives us one kind of piece of information that's not written in his law. Essentially what he's saying here is that you get the planet further away from the sun, we can show that it has to be moving slower out here, it has to be moving faster over here. So the closer you get to the object in which you are orbiting around, the faster you are moving. Okay? Now, the way of mathematically representing that is saying that we're going to sweep out a certain amount of area so you can factor in all the angles and everything else going on there. But essentially that's what he's saying here is that it's moving faster over here, it's moving slow over here, and it's a progression that it can be mapped out as we go. Okay? So let's actually take and jump over to this applet now and take a look at what's kind of going on. So I have it set up, this is Mercury, and here's the sun and Mercury kind of going around the sun. Okay. Keep in mind that Mercury is going to orbit around here, and we have this pattern. Now, if you watch, it definitely is moving slower here and faster over here. Okay, so it's moving slower here and faster over here, and this is definitely an elliptical orbit. Now, if we move up how elliptical this is, and go to, I can only go up to 0.7. Okay, so like Halley's Comet is even more elliptical than this, okay, to give you an idea of what we're talking about. But you see how this orbit is way more elliptical now. It's no longer Mercury. If we take a look at, say, Earth, and what does its orbit look like? And if you look, if I put the radial lines in, Earth's orbit is pretty close to a circle. It's not perfect, but it's pretty close to that, okay? We go to something else like Pluto, or, well, not Neptune. Let's go to Pluto, our first found dwarf planet. And if we look, there it is, okay? You might think that Pluto is not moving here, but it actually is. So if we show those radial lines, you might be able to see that very slowly the animation is moving. Well, the reason why is we're now talking about 10 astronomical units out here. So this is way further away than anything that we've seen before. So it's moving much, much slower, okay? So we had the speed of our animation was 0.2 years a second. So if I bring that up to 2 years every second, now we can see that movement a little bit more. So Pluto is a lot further away, but it still adheres to the exact same rules. Whereas it gets further away from the planet, it's going to slow down, and it's going to speed up as it gets closer, okay? Now, let's go back to Mercury, because that's probably the easiest one for us to see. It's going to look crazy here for a second until I bring down our speed again to something more realistic. Okay, and here's Mercury orbiting. And if we start to sweep out, let me turn these off. If we start to sweep out area, so if I click a sweep, and then if I click it again, we'll notice that every time I click to sweep it out, it's running a sweep, so basically 6.3% of the time, or 1/16th of a duration on here. So every one of these things is 1/16th of our time, okay? So the same amount of time, it travels further here, but it's closer, so it's got to be moving faster, okay? And that's what the law is telling us, is that the closer you get to the orbiting object on this side of the close side of the orbit, okay, we have it moving faster. If it goes over here, it's moving slower, okay? And you can do that for any of the swept areas that you're sweeping out as you take a look at that, all right? Those are those two laws. Now, conceptually, those two laws allow us then to dig into the third law, okay? So we know that we have elliptical orbit. We know that the planet moves faster when it gets closer to the sun, and it moves slower when it gets further away, okay? We know the area is equal here, which results in that. The third law dives us into this idea of, well, what is the relationship between those different planets, okay? And to go to this, I'm going to jump out to this applet instead. And just to kind of give you an idea of looking at only our solar system, if I zoom out, this is all the different things in terms of our solar system and how they are moving, okay? We have Neptune, Uranus, okay? We even have, this applet even has Eris, one of the most recent of our discoveries. In 2005, I believe, we found this dwarf planet, which is actually heavier than Pluto, but smaller. So you can see how elliptical Eris's orbit is inside here. This ellipse right here, this is Halley's Comet that's actually flying around inside there. So when you get down in close, let's zoom in on this guy here. You can see Earth and get to our terrestrial planets. We can see how elliptical Mercury is. But Earth and Venus and Mars are pretty circular, actually, in terms of their orbits. When we first were studying this, or when Kepler was working with this, we didn't know how far Earth was from the sun. Okay, we didn't know how far Mars was from the sun, but we could compare the speed at which Earth was revolving compared to Mars's revolution. So we knew the times. We said, hey, it takes Earth 365.25 days to get around the sun once. But Mars, by tracking its movement in the heavens, we could actually determine what its period of time was. Okay, so we knew Earth's period. We could figure out Mars by tracking it through the skies. So the question was, can we do a comparison between how fast Earth is moving and how fast Mars is moving to figure out how far away it is? Okay, and that's what Kepler did for us. So essentially, what he was able to show is that if you know the period of one body, so we'll call A our first object, okay, and you know the radius of that first object, that will be in comparison to the period of a second thing orbiting the planet and its radius, okay? Now, if you read through his actual statement, it gets kind of complex, but this statement then translates into this equation, okay? So what we're saying here is this: if you take the period of one substance in a ratio, so a fraction, a ratio to the period of another orbiting body, any satellite, any moon, any planet, okay? Those two things orbiting the same thing. So it'd be like Earth and Venus orbiting the sun, or it could be our moon and a man-made satellite orbiting Earth, but it has to be two things orbiting the same body, okay? If you compare those two periods and square that, it will equal the ratio of the two radius, or the two radii, cubed, okay? That's what he's saying. What that does for us is, if we say, hey, how much faster does Mercury orbit compared to us? Or how much slower does it orbit? How far away is it compared to us? We can start setting up comparisons between Earth and other planets. So that's where it kind of started. Now from there, we now know the actual distances, and we know the meters that they are apart, and we know their periods in more detail. But this is some of the first things we did. We used this equation to do comparisons of their period versus their radius. Okay, let's do a little practice problem with this now. Okay? So how far away from the sun is Mercury on average, because these are elliptical orbits? if the period of the object is 88 days. Okay, so we know that the Earth's period is 365.22 days, or sorry, 365.25 days. So if Mercury has a radius of 88 days, what is its radius? We also know that the radius from Earth to the Sun, on average, is 1.496 times 10 to the 11th meters. Okay, so let's take a look at this problem and solve it. All right, so you can pause the video here and then work it out, and then once you're done, hit play again, and I'll show you how we do it. Okay, so assuming you've tried to work this thing out, first thing we want to make sure that we can do is get our data, right? We need to know the period of one thing, we need a period of the other one, we need the radius of one and the radius of the other. So I have Earth versus Mercury here. Earth's period is 365.25 days. Mercury's period is 88 days. Notice, as long as I have the same time, we could do this in minutes, we could do this in seconds, we could do this in years. It wouldn't matter. If this was 1 year and we said what's the time for Mercury, it would be in Earth years would be the value there. So you could do it in any time. That equals our radius of each one. We know Earth's radius, we don't know Mercury's radius. Again, the same thing here. If we had this in kilometers and solve for this, it'd be kilometers in our answer. So whatever the unit is here, that's the unit that we're solving for. All right. Well, here's our equation. I factored in the squared into each one of these values and the cubes into these. And then I rearranged the equation. I'm solving for the radius of Mercury. So to do that, because Mercury is cubed, I need the cubed root of these values inside of here. Okay. If you're not super comfortable doing cubed roots on your calculator, remember a cubed root is the same thing as raising it to the power of 1/3. So the best way I have found to do a cubed root is to take your number and use your caret key or you raise it to a power and then just take 1 divided by 3 and then close your parentheses and solve it that way. Okay. There is a way to go in and get a cubed root function, but it's just as easy and quick, actually faster, to use the power button with 1/3. Okay, so try that. We plug it in, take 88 squared times 1.496 to the 11th power cubed, divide all that by 365 squared, and then take the cubed root of that whole thing, and we should get 5.79 times 10th to the meters for our radius of Mercury. Okay. Areas where students tend to struggle with this. One is finding these relationships, because sometimes the problem seems like it's giving you less information. But if you do that, take a look at it, because sometimes they give you the relationships. So they might say things like Mercury's radius is 1/2 of Earth's radius. So it's just a 1-to-2 ratio there. Or they might say it's 150% of Earth. So it would be 150 to 100 or a 1.5 to 1 ratio. Okay, so look for those ratio numbers when you're doing these problems. Also, another big problem I see is because we're squaring a bunch of stuff and cubing things and cube roots, there's a lot of algebraic and calculator mistakes that happen in these problems. Okay, so be very careful as you type things in. Use parentheses even if you don't think you need them to make sure everything types out the right way. Okay, and then last but not least, take a look and it doesn't make sense. 5.79 times 10 to the 10th meters. Okay, so that is smaller than this. Okay, well, its period is less, so it should be smaller. Okay, so that is reasonable that it'd be something times 10 to the 10th power here, considering where Earth is compared to Mercury. All right, guys, that finishes this video lesson. In our next lesson, we're going to talk about Newton and how he was able to take these ideas and take the next step in terms of understanding gravity. Thank you.